Hello and welcome back. Lecture 9-1, Impulse Sampling. Objectives: to define sampling and describe how it is used in signal processing, to summarize the various sampling methods and give a detailed process for solving problems using impulse sampling. Theory: if a signal is unknown, the process of analysis begins with acquisition of the signal. Acquisition means to measure and record the signal over a period of time. The most common technique of acquiring signals is by sampling. Sampling converts a continuous time signal into a discrete time signal. The sampling of electrical signals is most commonly done with the sample and hold and the analog to digital converter. Consider a signal x of t that is sampled by the following circuit. The switch closes for t seconds every ts seconds. Clearly, xs of t will have less power than x of t, and the amplifier is able to compensate for that loss. The result is still a continuous time signal, so you will need an A to D converter afterwards to recover the signal. The goal is to use sampling such that we can reconstruct x of t perfectly from xs of t. So here's the signal x of t, and here's the switch that it goes through. And then here's an amplifier, and this is xs of t. And as it stated earlier, a model for this switch opening and closing would be a pulse train, where the pulse train closes for t seconds, and it repeats every ts seconds. So if x of t is an arbitrary signal with the following shape, then xs of t would look like the following. It's a signal where this is the envelope for the original signal, and when the switch is closed, it copies the signal, and then when the switch is open, it's 0, and when the switch closes again, it copies the signal, and then when the switch closes, it's 0, and so on. So the width would be t, and it repeats every ts seconds. The switch sampler can be modeled by the following figure, where the input is x of t multiplied by p of t, our pulse train, and the output xs of t is equal to x of t times p of t. So as we stated earlier, p of t would be a pulse train, so it would be rect of t over capital T convolved with the summation from n equals -infinity to infinity, delta of t minus nts. So we would model that switch as the following. Here's your pulse at 0, at ts, at -ts, at 2ts, and so on, and the width of the rect would be t. Ideal sampling, impulse sampling. Impulse sampling or impulse modulation is the most ideal method to sample a signal, but it is not possible because we cannot generate impulses in the real world. It produces a continuous time signal whose value is 0 except at that sampling instant. The result is the sum of equal-sized replicas of the continuous time Fourier transform of the original x of t signal, each shifted by a different integer multiple of the sampling frequency fs and multiplied by fs. These replicas are called aliases. If t approaches 0 for the switch pulse sampler, we have an impulse sampler. So now p of t becomes the summation from n equals -infinity to infinity of delta of t minus nts, And xs of t, the output sampled signal, x of t times p of t, would be x of t is equal to the summation from n is equal to negative infinity to infinity, delta of t minus nts, or the summation from n is equal to negative infinity to infinity, x of t delta of t minus nts, which equals, at n equals the summation from n is equal to negative infinity to infinity, x of nts delta of t minus nts. So let's examine what this looks like graphically. So here once again, we have our signal, x of t. And it's an arbitrary wave. And then we're going to have our samples, xs of t. So here are the impulses. And these represent xs of t, where this one would be x of 0, x of ts, x of 3ts, 2ts, x of 3ts, x of 4ts, and so on. This is 0, ts, 2ts, 3ts, and 4ts. Or as a discrete time signal, x of n, it would look like the following, where this is x of 0, x of ts, x of 2ts, x of 3ts, and so on. So in the frequency domain, this becomes xs of j omega is equal to the Fourier transform of x of t times p of t, which is equal to 1 over 2 pi x of j omega convolved with p of j omega, which equals 1 over 2 pi x of j omega convolved with 2 pi over ts, delta, the summation from k equals negative infinity to infinity, delta of omega minus k, 2 pi over ts, or it's equal to 1 over ts, the summation from k is equal to negative infinity to infinity, x of j of omega minus k omega s. Note that omega s is equal to 2 pi over ts, is the sampling rate in radians per second, or fs equals 1 over ts is the sampling rate in samples per second, or hertz. Sampling theorem. Signals for which x of f is 0 for all frequencies greater than f sub m are called strictly band limited or band limited. If the aliases do not overlap, then the original signal could be recovered from the impulse sample signal by filtering out the aliases. So for example, here would be a signal that is strictly band limited. That means that it's 0 for values greater than fm or less than negative fm, which means when it goes through the sample or in the frequency domain, the aliases or copies could be filtered out so that only the original signal remains. For example, I've sketched an ideal low-pass filter here. The sampling theorem states that if a continuous time signal is sampled for all time t at a rate fs that is more than twice the band-limited fm of the signal, the original continuous time signal can be recovered exactly from the sample. If the highest frequency present in a signal is f sub m, the sampling rate must be above 2 times f sub m, and this frequency is called the Nyquist rate. That's when fs is greater than 2 times f sub m. A signal sampled at greater than the Nyquist rate is said to be oversampled. A signal sampled at less than the Nyquist rate is said to be undersampled. If a signal is sampled at a rate fs, the frequency fs over 2 is called the Nyquist frequency or bandwidth. Therefore, if a signal has a signal power at or above the Nyquist frequency, the aliases will overlap. A time-limited signal can also be band-limited. Conversely, a band-limited signal cannot be time limited. Based upon Fourier analysis, a signal can be unlimited in both time and frequency, but it cannot be limited in both time and frequency. The easiest way to see this is to think about when we did the Fourier transform of a rect. If a rect was time limited in the time domain, then when you take the Fourier, the sink in the frequency domain went on forever in both directions. Conversely, it's also true that if I have a sink in the time domain, which goes on forever in both directions, then it would be band limited in the frequency domain because it's a rect. Example 1. Find the Nyquist rate for each of the following signals. X of t is equal to 25 cosine 500 pi t. So the first thing we're going to do is to find the Fourier transform of x of t. X of j omega is equal to 25 pi times delta of omega minus 500 pi plus delta of omega plus 500 pi. So if I make a sketch of x of j omega, it has an impulse at negative 500 pi and an impulse at 500 pi, and the area under both would be 25 pi. So this means that the maximum frequency is 250 hertz. Remember, I get this because omega m, the maximum frequency in radians per second, is 500 pi radians per second, which is equal to 2 pi f sub m. So the Nyquist rate, Fs, would be equal to 2 times 250, or 500 hertz, which can also be written as 500 samples per second. B, x of t is equal to 15 rect of t over 2. So the first thing we do is find the Fourier transform. X of j omega is equal to 30 sinc of omega over pi. If we make a sketch, this is going to be a sinc that extends forever to negative and positive frequency with an amplitude of omega. So the sinc is not band limited. So what this means is that f sub m is equal to infinity because there is no maximum frequency. So f sub s is equal to infinity. Letter C, x of t is equal to 10 sinc 5t. So the Fourier transform, x of j omega, is equal to 2 rect of omega over 2 pi, omega over 10 pi. So if we make a sketch of x of j omega, it's a rect with an amplitude of 2 and a width of 10 pi. So the rect is band limited, and the maximum frequency in radians per second is 5 pi radians per second. And f sub m, the maximum frequency in hertz, would be 2.5 hertz. So the sampling frequency Fs is 2 times Fm, or 5 samples per second. D, x of t is equal to 2 sinc of 5,000 t times the sine of 500,000 pi t. So this is multiplication in the time domain. So to find the Fourier transform, it's going to be convolution in the frequency domain. So x of j omega is equal to 1 over 2 pi times the Fourier transform of 2 sinc of 5,000 t is 2 over 5,000 rect of omega over 10,000 pi convolved with j pi times the delta of omega plus 500,000 pi plus delta of omega minus 500,000 pi. And when you take the convolution, j pi divided by 2 pi times 2 over 5,000 becomes j over 5,000 times the quantity. So when you convolve these signals, it creates a copy of the rect at 500,000 pi and negative 500,000 pi. So we're going to have rect of omega plus 500,000 pi divided by 10,000 pi minus, note this should have been a minus here, so we're going to have minus the rect of omega minus 500,000 pi divided by 10,000 pi. And so if we make a sketch of this, it would look something like the following. The magnitude of x of j omega would be 2 rects, one centered at negative 500,000 pi, one centered at 500,000 pi, which makes this maximum value here 505,000 pi. So omega m would be 505,000 pi. F sub m would be equal to 252,500 hertz. Remember, omega m is in radians per second. So Fs, which would be equal to 2 times Fm, is 505,000 hertz. If the bandwidth of music is about 20 kilohertz, what should the sampling rate be? So music and speech, let's say, has the following form in the frequency domain. Where this is negative 2 pi 20k, this is 2 pi 20k, and this is actually in hertz. So omega should be an F. Then the sampling rate, Fs, should be equal to 2 times 20 kilohertz or 40 kilohertz. It must be at least greater than this, than this value. Since these are real-world values, we can use a CD as an example, or a compact disc player uses the sampling rate of 44.1 kilohertz, which would be obviously greater than 40 kilohertz. So now let's start the last example of today's lecture, example 3. Show the frequency domain result for sampling the signal x of t equals 3 cosine 2 pi 1400 t plus 30 degrees, and compare it to sampling y of t equals 3 cosine 2 pi 600 t minus 30 degrees. Let t equal nts, where ts is equal to 1 over 2,000 seconds, or fs is equal to 2,000 samples per second. So first, looking at x of t equals 3 cosine 2 pi 1400 t plus 30 degrees, we see that this has a maximum frequency, f sub m, of 1400 hertz. So the Nyquist frequency should be equal to 2 times 1400, which is equal to 2800 hertz. But the problem statement states that it's sampled at Fs equal to 2,000 samples per second, or 2,000 hertz, which is less than 2800 hertz, the Nyquist frequency. So what this tells us is that we are going to have aliasing. So writing the function for the sampled signal, x of n ts, would be equal to 3 times the cosine of 2 pi 1400 times nts plus 30 degrees. This should be degrees here, which equals 3 cosine 2 pi 1400 times n times 1 over 2000 plus 30 degrees, which equals 3 cosine 2 pi 7 over 10 n plus 30 degrees. And in the next step, we're going to subtract 2 pi n in order to get the fundamental or smallest possible frequency. So we're going to have 3 cosine 2 pi 7 over 10 n minus 2 pi n plus 30 degrees, which equals 3 cosine negative 2 pi 3 over 10 n plus 30 degrees. And because this is a cosine with even symmetry, we can write this as 3 cosine 2 pi 3 over 10 n plus 30 degrees. So now let's see what it looks like in the frequency domain. The original signal x of j omega is going to be 2 impulses, one at negative 2 pi 1400, one at positive 2 pi 1400, and the area under each would be 3 pi. So then, here's omega, and omega s is equal to 2 pi 2000 radians per second. So now let's look at what the sampled signal looks like. So first, once again, I will draw my original signals, which was at negative 2 pi 1400 and 2 pi 1400. And then I'm going to make my first copy. So my copies are going to be centered around omega s equal to 2 pi 2000 and negative 2 pi 2000. So when it was centered at 0, I had an impulse at 1400 and negative 1400. So when it's centered at 2 pi 2000, I'm going to have an impulse at 2 pi 3400. And an impulse at 2 pi 600. So this is what we call aliasing, because I now have overlap between the original signal and the impulses from the second sample. Same over here, I'm going to have an impulse at negative 2 pi 600 and one out here at negative 2 pi 3400. So what if I then sampled again at 2 pi 4000? At 2 pi 4000 minus 1400, that means I will have a sample here at 2 pi 2600. So that's more aliasing. And I would also have one over here at negative 2 pi 2600. And remember, these last two come from the sampled signal at 2 omega s and negative 2 omega s. So now remember, in the problem statement, we want to compare this to sampling y of t is equal to 3 cosine 2 pi 600t minus 30 degrees. Once again, we are sampling at 2000 hertz. But in my new signal, the maximum frequency is 600 hertz. So the Nyquist frequency is 1200 hertz. So now Fs is greater than 1200 hertz. So there should be no aliasing. So first, what does my sample signal look like? I have y of NTS is equal to 3 cosine 2 pi 600 times n over 2000 minus 30 degrees, which equals 3 cosine 2 pi 3 over 10 n minus 30 degrees. So the first thing I want you to notice is that this expression is the same as this one. So what this tells me is that x of NTS is identical to y of NTS when sampled at 2000 samples per second. So what this tells me is that the aliases make x of NTS look like y of NTS. And that's not good because you're not going to be able to retrieve the original x of t at this sampling rate. So let's see what this looks like in the frequency domain. So here's our vertical axis, y sub s of j omega, and our horizontal axis omega. So then we have our first sample, which is the Fourier transform of 2 pi 600t minus 30 degrees. So that means I'm going to have an impulse at 2 pi 600 and an impulse at negative 2 pi 600. The area underneath would be 3 pi. And remember, even if the amplitude's not the same, you can always use an amplifier to get that part. So then our next sample would be at omega s equal to 2 pi 2000. And then here's the one at negative omega s equal to negative 2 pi 2000. So that sample is going to have copies that are 600 away from 2 pi 2000. So there's going to be one at negative 2 pi 1400. And one at negative 2 pi 2600. And then over here, I'm going to have one at 2 pi 1400. And 2 pi 2600. And note that there is no aliasing. So if I was to go on and draw the next samples would be at 2 pi 4000 minus 600 would put a copy right here at 2 pi 3400 and a copy down here at negative 2 pi 3400. And what you should see here is that although maybe not to the same scale, all of the copies are at the same locations: 2 pi 600, 2 pi 1400, 2 pi 2600, 2 pi 3400. And the same on the other side. So in the frequency domain, these look identical. So if I use a filter, for example, to try to get the original signal back, and if my filter cutoff was at omega s, then an ideal filter would be right here. And the signal that I would retrieve would look exactly the same for both. So I could not reconstruct x of t because it would look like y of t. And this concludes lecture 9-1 on ideal sampling.